In 5.2, as we look at multiplying polynomials, multiplying by a polynomial, meaning more than one term for both of your polynomials. Again, the key is really about distributing, and the key is really here, something I didn't focus on when we first saw the mixed trick on the previous page, but drawing an arc from every term in the first polynomial to every term in the second polynomial. That's the key. Whenever we had a single term out front, it was just that one term distributed to every term on the second polynomial. Here, just start with your first term, this x in this case, and draw arcs to both terms, to every term in the other polynomial. So that first arc is an x times an x. Well, it's an x to the first times an x to the first, and 1 plus 1 is going to give us 2, right? Multiplying same bases, add those exponents. Do not lose that. It's a very common mistake to call that just x. We got to add 1 and 1 to get 2. Now here you get x times a 3. There's really nothing to do except put them together as a plus 3x, right? That's just the order we write them in, number then variable. So x times 3 is just 3x. Now this one is done. We've distributed both arcs. When I go to draw these arcs, I'll draw them below, and I want to really emphasize this is a -2 that we're going to be distributing. So -2 times x is a -2x, or minus 2x, and the -2 times the 3 would be a -6, so minus 6. So you take each term, and you draw arcs to every term in the second polynomial. Notice we drew 1, 2, 3, 4 arcs for 1, 2, 3, 4 terms. However, we're not done necessarily. We do want to look for like terms to combine. X squared, I see no other x squareds, so I'll bring him down. But I've got a 3x minus 2x, right? Both are just x terms. So 3 minus 2 would be a 1. You could put 1x or just x. And then the constant of minus 6 comes down as well. And that's it. That's our combined like terms for our final answer. So we'll just keep doing that for the next several here, starting with, in this case, the first term of 2x, distributing that 2x to both those terms, 2x times 3x. So 2x times 3x, we can take the 2 times the 3 and get the 6. And then it's x again, same as this first one, an x term times an x term, x to the first and x to the first. You combine the 1 and 1, you add them to get x to the second. 2x times the 2. All we have are the numbers. 2 and 2 multiply to give you a 4. The x kind of tags along, and that 2x is done. If you can hear that in the background, that is my dog Sparky drinking up some water. Just so you're not worried I don't have a leak in my house anywhere. So -3, we're going to distribute that below. -3 times 3x, -3 and 3 gives me a -9, and the x comes along. And then -3 times 2, -3 times 2 is -6. Again, 4 arcs for 4 terms, then combining any like terms. That's the only x squared term I see. But we've got a couple x terms. 4 minus 9, so a -5, so minus 5x. Bring down the -6. And done. All right, next one. Start with a 3. 3 times 5, 15. And 3 times -3y. 3 and -3 is a -9, so -9y. That's done. 3 is distributed. Positive 2y. 2y times 5. 2 and 5 is 10, so plus 10y. Now the 2y and then -3y, so positive 2 times -3 is a -6. And y times y, again, y to the first and y to the first multiplied, 1 plus 1 gives you y to the second. So, again, looking for like terms. That's my only constant, 15. There's a couple y terms, -9, but plus 10 would be a plus 1y. And minus 6y squared. That would be correct, all terms combined. And if you wanted to put it in that order we've talked about, and we mentioned we'd see a lot, the y squared, then the y, then the no y, right? Y squared y and a constant. That would work. Again, this is perfectly fine as well. But Going forward and knowing what we're going to see a lot of even in the next chapter, I would suggest making sure you see this pattern if it's there. It's not always there, but if it's there, and it has been for our last 3 examples, notice, x squared x no x, x squared x no x, y squared y no y, that's important. We're going to come back to this idea of multiplying these binomials, and not just any 2 binomials, but ones that are in these kind of forms here. We're going to come back to this pattern being very important in a later chapter. All right, so more of that to come. The last example here on this page, though, notice it's a binomial and a trinomial. It doesn't change a thing about what we do. All it does is add more arcs. This x, first arc, x times 3x squared. Remember, this is a 1, right? 1 out front, and this is a 1 up top. So 1 times 3 is 3. X to the first, x to the second. 1 plus 2 gives me x to the third. Next arc, 1x times negative 5x. 1 and negative 5 is a negative 5. X to the first and x to the first is going to give me x to the second. And then 1x times 4. 1 times 4 is 4. And the x pretty much just comes along. So first term has gone to all 3 of those. Now we'll use this positive 2. Taking it below, 2 times 3 is 6, and there's still the x squared. 2 times negative 5 is negative 10, and there's still the x. 2 times 4 is 8. So notice in this case we drew 1, 2, 3, 4, 5, 6 arcs for 6 terms. A nice little pattern to point out here. For all the others that we just did, the binomial and binomial, 2 terms times 2 terms, 2 times 2, told you there before. 2 binomial and 3-term trinomial, 2 times 3 is 6. So you can actually just multiply the number of terms times number of terms and know how many terms you're going to get initially, how many arcs you're going to draw, but then they're still combining of like terms. So that 3x cubed is the only x cubed, but we've got minus 5x squared plus 6x squared, so that'll be plus 1x squared, and then we've got 4x minus 10x, so minus 6x, and then bring down the constant, and there would be our completely simplified and all like terms combined final answer.